Happy Monday.
I guess it is.
Morning.
Morning?
It feels like morning.
Yeah, I guess it does. Okay.
Good afternoon, not good morning.
Okay, so I was going to, well, I have one announcement, I guess. It's about the quiz or quizzes, like moving forward. So we just had a quiz on Thursday. We're gonna have another, we'll have the exam next week. So I kind of figured it'd be better to do the next quiz on Thursday instead of today because
I thought the exam was this week.
I also
it
thought
was
the exam.
originally, yeah, I moved it to next week. Yeah.
Okay.
Yeah. So it will be next week in class on Thursday. And then there will be like another break day that falls on a Monday. So I was kind of just thinking of moving quizzes to Thursdays instead of Mondays, just because it will like work a little bit better with our schedule going forward. So if that's okay with you guys, I'll just like switch that. Okay, cool. So I'll update the Canvas page so that it's on there as well. But so our next quiz will be on Thursday. Let's see, the last thing we covered was, let's see, what was on the last quiz? I believe, okay, let me just actually
Was the
find
last quiz solution sets?
Yeah, I think so. I think our next quiz will be on like transformations, linear transformations. So we've talked about those for a couple sections now. But I'll definitely put that info on Canvas so you can see it for next time. Yes, these solution sets, great. Okay, cool. Also the other thing was, oh yeah, linear independence too. The other thing was the problem session. So I don't think anyone showed up last week. So I was thinking of just reusing the same problems. I'm not sure, did anyone like complete them on their own?
I attempted them, but I wasn't able to fully complete it.
Okay, so then even if you've already attempted, you can show up to the problem session and get some questions answered and maybe finish it from there. So
sorry.
Yeah, go ahead.
I was also curious if you have any advice on how to study for the exam, because like there's a lot of information and like equivalent statements and like different ways of thinking about things, and I'm having a really hard time keeping it all straight. Like non-trivial solutions and pivot columns and linear independence, and it gets all jumbled up in my head.
Yeah, I know. And so that's the thing, is all of these ideas are very interrelated, so that can be the confusing part. But I will post a study guide and I'll give some like suggestions on how to study. But usually with any math class, like the best thing to do is just to work with problems, like actually, work with the definitions, try to use them in context, like that kind of thing. Because like just staring at a definition and not actually trying to do something with it is not as good. It's not cool, right? But yeah, I'll definitely post that. It might be tomorrow, not today, but I'll work on getting that up soon. So let me write myself a note because otherwise I'll forget. Okay, so let's get started on the new material. So we were almost done with we were almost done with section 1.9, so we just need to finish up. I just want to write out all of those equivalent statements for being one-to-one, and then we'll move on to 2.1. Okay. Oh, oops. I need to pull this up. Okay. So the last thing that we did was we showed that, so I'll just write this down. This is where we ended last time. We had this theorem that said that T, so a linear transformation, maybe I should put that, that's important information. So a linear transformation T is 1-to-1 if and only if you have that this equation, so T of x equals 0, the 0 vector, has only the trivial solution. Okay, and so we showed why that was true, and now we can give a list of basically what it means to be 1-to-1 and all of the different ways we can think about that. So 1-to-1 transformations. So if we're looking at, okay, actually, let me put it this way. So let T, which maps Rn to Rm, be a linear transformation. And A be its associated matrix. Right. Then the following are equivalent. So the first thing is that T is 1-to-1. So all of these other bullet points will be equivalent to that. So we said that, well, first of all, this theorem right here tells us that T of x equals 0 has only the trivial solution. That's equivalent to T being 1-to-1. Another way we can say this is that for every B in Rm, T of x equals B has at most one solution. That's the definition, but so it is either unique or inconsistent. Also, we can look at just the matrix that describes this linear transformation, so that associated matrix A. And if the columns of A are linearly independent, so let me put it this way, then T is 1-to-1. Okay, so maybe we should say why that might be the case. So the columns of A are linearly independent. What that means is that, so we can write AX as just x1 times the first column of A, x2 times the second column of A, and so on. this would be A2 all the way up to, there are n columns because A is an m by n matrix. So we end with xn, an, right? Now, if we set this equal to 0, the columns of A being linearly independent, so if columns are, I'm going to abbreviate linearly independent with Li, if that's okay. If these are linearly independent, that means that this equation has only the trivial solution. That comes from the definition of linear independence. This is only the trivial solution, but this is exactly the same thing as saying t of x equals 0 vector, right? There's really no difference in these two equations. They're saying like exactly the same thing, right? So that was one of our equivalent things up here. That means that t is 1-to-1. Right? Does that make sense so far?
Could you also say, more for purposes of solving problems, that A must have a pivot in every column?
Yeah, exactly. That was the next thing I was going to say.
Oh, oops, sorry.
No, you're fine. No, that's good. So yes, it is true that the most useful way to think about this or try to figure out if t is 1-to-1 is to just look at the pivots, right? So this is, A has a pivot in every column. Right? If that's the case, then t is 1-to-1. And then, did I cover everything? Okay, one more. We can say that the range of t has dimension n. Right? So meaning that it has the same dimension as what you started with. So remember that t maps Rn to Rm. So in particular, notice that that means that m has to be greater than or equal to n in order for that to be possible. Otherwise, this target space is too small to hold the range having dimension n inside of it, right? So there's some things we can say about being 1-to-1 and onto, so similar ideas here. So looking at a linear transformation from Rn to Rm, right, we do not have a quiz today. It'll be on Thursday. Okay, so if t maps Rn into Rm, it cannot be onto, or we'll start with 1-to-1, cannot be 1-to-1 if we have what relationship between n and m?
If n is greater than m?
Right, exactly. If n is greater than m, then our domains, or sorry, our target space is too small for the function to be 1-to-1, right? And then going the other way, this cannot be onto if n, so it'll be the other way, if n is less than m. So in that case, remember that onto was saying that everything in the target space gets hit by the function, right? And if you're starting from somewhere smaller than the target space, you don't have enough like mass to cover the target. So you don't have enough space in the domain to cover the target. And another way you can think about it is in terms of the matrices. So I'll make a little space here. So if you look at the matrix A, in order for it to be one-to-one, it has to have a pivot in every column. And that can only be the case if you have it. Oh, these can be equal. This is possible to be equal, sorry, like that. So a pivot in every column, meaning that you have to have at least as many columns as you have rows, right?
I think you were correct the first time. So it cannot be one-to-one if n is greater than m, and it can be one-to-one if n is less than or equal to m.
You're right. Okay, so undo that part. Yeah, there we go. Okay, so A has a pivot in every column. Okay, so wait, I don't want to state this in this way. Okay. Let me think about how to write this. Okay. Okay, if one-to-one, A has a pivot in every column, which is not possible if the number of columns is greater than the number of rows, right?
Because then you'd get a free variable and
Yeah, exactly. Yeah, greater than number of rows. Okay, there we go. And then similarly, if onto, then A has a pivot in every row. So not possible because, or not possible if you have that your number of rows is greater than your number of columns. Okay. You can have, so you can think about the fact that a function is one-to-one if you have a pivot in every row and onto if you have a pivot in every column. So you could think of a matrix that has a pivot in every row and every column, right? So it is possible to have both for T to be one-to-one and onto. But if that is the case, then it has to be mapping Rn into Rn, or another way of saying this is that A has to be a square matrix. Did I define square matrix? Yeah, okay, so this means same number of rows as columns.
wait, so if a transformation is one-to-one, isn't that basically guaranteeing that it's also onto?
No, so they're not the same thing. One-to-one is saying that you don't have any collapsing, right? And onto is saying that everything in the target space gets hit by the function.
Oh, okay.
Yeah.
So are the only linear transformations that are isomorphisms also automorphisms of Rn?
I don't remember the definitions of those. Let's see. So an isomorphism for us would be one-to-one and onto, I think.
Yeah, so since if the kernel is trivial, then it's going to be one-to-one.
Yeah.
So,
right.
So yeah. So it has to be mapping from Rn to Rn to be
Oh, okay. I see. So
isomorphism.
it has to be an automorphism. Yes, that's right. Yeah. And I mean, if you think about it, it makes sense that if you have an okay, so I know not everybody's following this, but if you have an isomorphism, it's preserving the linear structure. And if you were to map into like a higher dimensional space or a lower dimensional space, it's not really the same structure, right? So it makes sense, yeah. Okay, so we are now done with section 1.9 and we're gonna move on to 2.1. So this is called matrix operations. So we're going to be talking about basically different operations that we can apply to matrices. The biggest one being multiplication. So how do we multiply two matrices? So first, let's look at how we represent a matrix. So we're going to have a way of referring to particular entries, right? So how we refer to specific entries in a matrix is by their row and column, right? That uniquely defines what entry you're talking about. Okay. We always put the row first and the column second. So that in the same way that we say A is an M by N matrix and we say the number of rows first and then the number of columns. When we're referring to entries, we say the row first and then the column. So if we're representing a matrix, the very first entry, the one that's in the first row and first column, we'll label 1, 1, right? So A, 1, 1. So the first one is for the row, second one is for the column, and then the one that's in the first row and second column will be 1, 2. And if we have n columns, then we'll stop at 1n, right? And then we continue with this pattern. So second row, first column. So that will be A2, 1, A2, 2, and so on, right? And then we'll have m rows. So look like this. Get AM2 and AMN is that entry in the last row, last column.
And me, I'm a little confused. I thought N was the row and M is the column.
We use M for the number of rows. Right, so this is M and N for columns. Is that what you said? M.
Oh, I thought it was N was the rows and M was the columns because it's an N times M matrix.
This is an M by N matrix.
Oh, I've been doing it wrong this whole time.
No. I think this is the nth column, the last column.
Mm-hmm. Yeah, this is the nth column.
This is the nth.
And this
Okay.
is mth row.
Okay, sorry.
Okay. Yeah, no problem. I mean, it's really, you could call it whatever you want, but it's nice to be consistent, right? So you don't get mixed up. Okay, so this is our matrix. This is like how we'll represent it for an arbitrary matrix. And then if we want to refer to a particular entry, we just, give its like sort of coordinates, right? Okay, so there are particular entries that are important. So the ones that are where the number or the row matches the column. So A11, A22, and so on. These are called the diagonal entries. And they lie on the main diagonal. So. One sec. What do you do if a matrix is 10 by 12? So it would look like, oops. Go back. Oh, there we go. Okay. Okay. Let's see, 10 by 12. 10 by 12 matrix. That would have 10 rows, 12 columns. So you would just construct it this way. It'd be like A11, A1, 2, 1. Okay. And then you would just continue down and you would stop with, so it has 10 rows. So it would be 10, 1. Yeah. And then A1, 2, and so on. Stop with A1, 12. I just put the comma there so that it's like clear what that is. Does that kind of make sense? How this would work? I didn't fill in all of the entries, and it would be, so it would have more columns and rows, so it would be rectangular, but yeah.
So this would only have 10 diagonal entries, and the diagonal entries would be A11 through A1010.
Exactly. Yeah. Yeah. So I was gonna give a little picture of that. So maybe I'll get rid of this. Yeah. So the main diagonal, if we want to just picture, so say we construct a matrix that looks like this. Just have some numbers in it. The main diagonal, this is a square matrix, so the main diagonal will just be like straight along here, right? Like that. Oh, oops. And if you have a rectangular matrix, you still have the main diagonal, so it'd be 0, 2. Okay, so say your matrix looks something like this. The main diagonal, oh, what did I do? Okay, I'm just gonna delete this. There we go. I wanted a rectangular matrix. So the main diagonal stops when you get to this point. So you've run out of columns, so it stops right there. Right. Okay, so so far we've defined diagonal entries, the main diagonal, which is just like carves a line through your matrix. Always starts at top left. Yeah, exactly. It always starts from that very first entry, the first row, first column, and then you just follow it down, right? Okay, so we have, if we do have a square matrix and it is 0 except along the diagonal, this is what we're going to call a diagonal matrix. So a square matrix with zeros off of the main diagonal is called a diagonal matrix. So for example, if you have something like this is a diagonal matrix.
So row reduced echelon forms would be a form of this.
Yeah. So the reduced row echelon form should be diagonal so long as you're dealing with a square matrix. So we don't talk about it unless we have a square matrix, even though we can define the main diagonal for non-square matrices. Okay, but yes, that's true.
Is that like only possible if like there's a pivot in every row and every column?
Ah, right. So if you don't, let's see if you, so you can have, yeah, yeah. So there's an issue there. It's not exactly true, because you could have something that was yeah, like this, and then yeah, this is in reduced row echelon form, but there's a one that's not on the diagonal, right? So I guess I was not exactly right about that. If you do have a pivot in every column or every row either, then yeah, it would work. But then I think it would always have to be the identity matrix. So yeah. Yeah. Okay. Okay, so this is diagonal. This is what we call a diagonal matrix. Another particular type of matrix. So we talked about the identity matrix, but I'm not sure I mentioned this. So the matrix whose entries are all 0 is called the 0 matrix. Just like the 0 vector, just the 0 matrix. And okay, so now that we've talked about these properties of matrices, or not even properties, but just like how we're going to talk about matrices, we can talk about multiplying by a scalar. So when you want to multiply a matrix by a scalar, so how you do this is you multiply all of the entries. So maybe I'll put it this way. To multiply a matrix by a scalar, you multiply all entries by that scalar. So everything. Oops. So for example, if you have 2 times the matrix 1, 2, 3, 4, then that will give you 2, 4, 6, and 8. So multiply each entry by that particular scalar. And then adding matrices, it is pretty natural. So to add 2 matrices, you just add the corresponding entries. So they have to be the same exact size in order to be able to add them. First, they must be the same size. And in order to add them, you add the corresponding entries. Right. So for example, if you take 1, 2, 3, 4 and add 5, 6, 7, 8, then your first entry is just 1 plus 5. This guy is 2 plus 6, 3 plus 7, 4 plus 8, and then you can just simplify this. So we get 6, 8, 10, and 12. There we go. There we go. Okay, so these are pretty natural. Matrix multiplication is going to be a little bit more involved. So we'll get to that in a second. So there are these different properties of matrix addition. They are also pretty natural. So they're basically what you would expect. And they're really similar to the vector properties that we talked about. So properties of vector addition. And multiplying by scalars, but yes. So this is interchangeable. So A plus B equals B plus A. It's associative, so we can add A and B first, or we can add B and C first. So A plus the zero matrix, so we'll just represent the zero matrix with a zero. And hopefully it'll be clear from the context what we mean by that. So if we add the zero matrix to a matrix, it gives us back the zero matrix. We can distribute scalars. So we're just using R because this is what they use in the book. But so R is a scalar, just a real number. And we can multiply each matrix in turn by that scalar. If we have, just A. Two scalars, we can apply the scalar first and then add, or I don't know, that wasn't the right words, but this one. And then if we have something like this, we can first multiply the scalars and then multiply by the matrix. Okay, so these are all basically what you would expect to be able to do with this from the definition. So it's not too hard to justify these to yourself. Let's talk now about matrix multiplication. Okay, so if we want to multiply two matrices, so say we have a matrix A that is M by N, and a matrix B that is N by K, then we can multiply them together. The reason being that the number of columns of A matches the number of rows of B, so this N is the same. And that's just because of the definition. So let's write down the definition. So I'm just going to rewrite B as its columns. So we'll just call the columns of B, like B1 up to BK. Right?
Can I ask a quick question?
Yeah, go ahead.
In properties of matrix addition, what are the R and S? Like I know like A and B is like matrices.
R and
but-
S are real numbers.
Oh, thank you so much.
Yeah, no problem. Okay, let's see. Okay, so we've just rewritten the same thing. But so for our definition, so this is really like our definition of matrix multiplication. This is going to be just the matrix where the columns are the matrix A times the first column of B. The second column will be the matrix A times the second column of B, and so on. So we just fill in each of these up to BK, right? And we already talked about how to do the multiplication of a matrix times a vector. So we're just using that to define this, to define the multiplication of two matrices. Great. Okay. So it's important that, so I said this already, but it is important that the number of rows number of columns of A to match number of rows of B.
I have a question.
Yeah.
What part of the definition are you using to bring A into the set of vectors?
So that really is the definition.
Oh, it literally just is the definition.
Yeah, it is.
Okay,
Right. So we could say
thank you.
AB equals this. Yeah. Right. So like I was saying, we need the number of columns to match the number of rows of B. So up here, we did say that A was m by n. That's the number of columns is n. Number of rows of B is n. If that does not happen, then this multiplication is not defined, right? Okay. And then the other thing I'll mention is that our result is going to have, so if A is n by n and B is n by k, A times B, the result that you get will be a matrix that is m by k, right? So you'll end up with m rows and k columns, right? Okay. Maybe I'll do this, color code this, so m by k. So let's do an example of computing this. So say we have A is 1033 and B is 2143, right? So to figure out what the columns of A times B are going to be, we just compute separately A times B1 and A times B2, right? So B1 is just going to be that first column, so it'll be this right here. So we'll take 1033 times 2, 1. And then we already learned how to do this. So we multiplied the first entry of the first row by the first entry of that column. So we get 2. And then we move on to the next entry of the first row multiplied by the next entry of the column vector, and then add that to the first thing. So add these up, do the same thing for the second row. We get 0 plus 3. So this will give us 5, 3. Okay. And then we also want to compute A times B2. So that same matrix A and 4, 3. And so this part is going to be 4 plus 9. And the second entry is 0 plus 9. Okay, so we computed those two vectors and then we just stick them into a matrix to get our answer. So A times B is going to be 5 times 3 for the first column and 13 and 9 for the second column. Okay. So this was just using the definition, right? So we exactly used the definition of A times B, but there is a more practical way of computing A times B that will be a little bit faster. But this way is going to be more condensed, and so it's going to be easier to make mistakes. So just be careful when you're computing. So here we have A times B. I'm going to write out these sort of general matrices, and this is just going to be for us to picture how to do this. Okay, so this might take a while. So we're going to start with, so if we have A times B, where we just have general matrices A and B. I'm gonna draw this way. So I want to insert the ith row. So here I have I, and the column is 1, and M1. Okay, so this is going to be, so this is the pth column that I've written here, this one right here. And then it will end, so that's just an arbitrary column in the middle. And then it will end with 1n. This is, oops. This is in, and then the last entry is mn. Okay, and hopefully there's room for B. So B being a, so if A is m by n, B will be n by k, because the number of columns, sorry, yeah, number of rows of B has to match the number of columns of A. So here I want the, so I'm just using a random letter, so it'll be L, BN1, B1J. This will be BLJ. BNJ. B1K. Okay, yeah. So I was thinking of typing this out instead of like making myself and you write it, but it would have been a nightmare because this is actually really hard to do. So I decided to do this instead. So I'm sorry that it's so tedious, but the idea here, what I really want to get you guys to picture is that we have this ith row, right? So this is the ith row. Maybe I'll do that in a different color. So right here. So we're focusing on the ith row and the jth column, and these will determine the entry in the product. So jth column, that is ij. So we'll have M1. I'll just fill these in a sec. So this will be I1, IJ, MJ. IK, MK. Okay. So that should all be correct. So looking at this, so saying that this matrix with all the C's in it represents the product, what we'll get in the end once we do the multiplication. The ith row and the jth column, they determine just that entry ij, right? So, and how you get that Cij is you take the first entry in the ith row. So this will be equal to AI1 times the first entry in the jth column. So B1J, right? And then you move on to the next one. So it would be AI2 times B2J, and so on until you end with the last entry. So B, N, J, yeah, it'll be like that, which we can write as a sum if we wanted to. So using K for a variable, this is I, K times B, K, J. Okay, so we can write it down this way, but more clearly, we can just say to find Cij, we multiply the ith row by the jth column. And when I say that, I mean we just multiply the corresponding entries. Corresponding entries and add. Right? So when I say multiply the ith row by the jth column, this is what I really mean. If you know what a dot product is, it is the dot product of the ith row with the jth column. If you don't know what that is, that's fine. It's just what we described. Right? So this is the same thing as what we use to define the matrix times a vector, right? So same idea. And it will make the computation a little bit easier and more compact. So if we do an example, so say we have a matrix A, which is 3, 1, 5, and 2, and B, which is this guy. So this matrix is 2 by 2, the first one, A, and the second matrix is 2 by 3. So since these twos match, this multiplication will be defined, right? So first AB is defined. And so let's go ahead and compute it using this idea. So we have 3, 5 minus 1, 2 times 2, 1, 0 minus 5, 2, 3. And so I'm just going to focus first on the first entry, right? So we would take the first row and the first column from the second matrix, and we multiply the corresponding entries. So we get 3 times 2 plus 5 times 1, right? And then we fill in the other stuff, but we'll do that in a second. Right? So we would get 6 plus 5, so this would reduce to 11. And then let's pick another entry to fill in. Maybe we'll do this, this one right here. So this is in the second row, second column. So we want to focus on those. So I'm just gonna highlight them in a different color, like that. And what we'll get there, if we multiply the corresponding entries and add that up, we would get 0 minus 10, right? So it would just be negative 10, right? Okay, and then we can just continue to do that for all of the other entries. And if you work this out, you should get, let's see, 11, 0, negative 25, negative 10, 21, and 4. Okay, so that is matrix multiplication. Some important things to note about it. Okay, let me just say you should check this yourself. Now, important things about this. Something that is very different from regular multiplication of numbers is that, exactly, yeah, order matters when it comes to matrix multiplication. Yes. A times B is not the same as B times A, right? I mean, in general, it possibly could be, but in most cases it's not. So even in our example, if we tried to compute B times A, that would not even be defined, right? Because we would have more columns in B than we have, wait, so we would have more, anyways. We need, so if we did B times A, we would have 2 rows, 3 columns, and A has, so B has more columns than A has rows. That's what I was trying to say.
So in this case, you can't even multiply them. It would B times A.
Yeah, yeah. So maybe I'll write that here. A times B is defined, B times A is not defined. Yeah. Yeah, so when you're doing matrix multiplication, you should check before you even compute anything that the multiplication is defined, right? Okay, so this is important. This is something that you might expect to be true, that you could multiply them in either order, but it's definitely not the case here. Another thing is that A times B equals A times C does not mean, so if you have this, it does not mean that B equals C, right? Okay, so you can't just like cancel these two and get B equals C. So that doesn't work for us. So just as an example, if you take 1, 0, 0, 0 times 1, 2, 3, 4, you would get, so doing the matrix multiplication, you would get 1, here you would get 2, and in the bottom you get 0 and 0. And you could do 1, 2, 4, 5, 6. So that's a different matrix than the first one we used, but we'll get the same answer. So you can see that these are the same, but these are not. It's hard to, but say, but 1, 2, 3, 4 does not equal 2, 5, 6. Wait. And then one last thing, if you get A times B equals the 0 matrix, so here this means the 0 matrix does not mean A equals 0 or B equals 0. So this would be true for real numbers, right? If you got the two numbers being multiplied together or equal to 0, then either one of them has to be equal to 0. But this does not work this way with matrices. Okay.
So like in fact, like A and B can both not be a 0 matrix, and you can still get.
Yeah. So you could have something, I believe, like this. You should get, right, 0, 0, 0, 0, right? But both are non-zero. Okay, so we have some properties that do hold for matrix multiplication. So let's do, let's write those down. So it is associative. So we could do, oops. A times B times C. That would be the same as A times B times C, like that, right? Also notice when we're writing matrix multiplication, we don't write anything between the matrices. There's no like dot or times or anything. It's just we write the first matrix, then the second matrix, and that means we're multiplying them together. Okay, and then we have a distributive law, right? So if we're multiplying B plus C on the left by A, so A is to the left of this sum, then we get A times, oops, B. This is equal to A times B plus A times C. Since this will not be the same as multiplying by on the right, because it matters what order we multiply in, we have to also write it this way. So this is also true. We can distribute from the other direction as well. So B times A plus C times A. But you see that this would not be the same as the first thing because order matters again. So these are referred to, this would be the left distributive law. And this would be the right distributive law. We can multiply by scalars and they behave pretty nicely. So we could take a scalar times the product of two matrices, and that would be the same as multiplying the first matrix by that scalar and then multiplying by B. And it would also be the same as multiplying the second matrix by that scalar and then multiplying A and B, or the new B together. Right. Okay. And then if you multiply by the identity, you get the same matrix back. So if A is an M by N matrix, and we multiply on the right by the identity matrix of size M, we get A. And if we multiply by, on the left by the identity matrix size N, then we get A itself back. But if A is a rectangular matrix, so it doesn't have the same number of rows as columns, then depending on which side you're multiplying on, you want a different size. So it's just whichever one makes this multiplication actually work. Okay. So we end at 150, is that right? Okay, I think that's right. Stop me if I'm wrong. Okay, so these are our properties. Now there's an important connection between matrix multiplication and linear transformations. So we're going to talk about that now. And so it will correspond to compositions of linear transformations. Let's see. Yeah, so I'm going to post a study guide hopefully by tomorrow. And I'll put out an announcement when I actually do that. Okay, yeah, no problem. So let's think about first two linear transformations, and we know how composition works for just regular functions. It's the same for linear transformations. So if we consider to linear transformations. So let's say T from Rn to Rm and S from Rk, Rk to Rn, right? Okay, so if we want to compose these two, we want to make sure we compose them in the right direction, right? So that this is actually well defined, makes sense. So just picturing what's going on, we have Rn and T maps that into Rm, right? And then S maps Rk into Rn. So it would be like this, Rk, right? And the composition is going to apply one and then the other in succession. And so it will start at this domain, and the codomain will be Rm. So it will go from Rk to Rm, right? And we have to do it in sort of the opposite order of what the picture shows, right? So we first apply S, that will get us from Rk to Rm, N, that is, and then we can apply T, which will get us from Rn to Rm. Okay. So we have this transformation. This is the composition of T with S. And if we know that these are linear transformations, so we know that we can represent them using matrices, right? So let me put it this way. So suppose that T is given by, I'm actually going to use Y as my variable for this one. Okay, T of Y is given by A times Y, so the associated matrix is A, and S of X is given by B times X, right? Then if we look at the composition, T composed with S of X, just writing out what that means, we first apply S to X and then apply T to that, right? And we know that S is given by multiplication by B, right? So we can just rewrite that as B times X. And then we know that the composition, so when we take T of B times X, that's the same as multiplying that by A, right?
I'm sorry, I'm a little confused.
Okay, so which part are you?
How do you get from T times S with T and S being matrices
Mhm.
times X the vector equals T function S function X? Is that just by definition?
Right, yeah, so I'm just rewriting this. So it's just like how like compositions of functions usually work, right? So you can write it this way.
Okay, so the T and S themselves aren't the matrices.
They are not the matrices, yeah, they're the functions.
Okay, thank you.
Yeah, no problem. Okay, so what we get in the end is that T composed with S is the same as writing or multiplying by A times B. So multiplication of the two matrices that describe T and S correspond to the matrix for the composition. So we have this like correspondence between composition of linear transformations and multiplying two matrices. And
The X vector, you multiply X vector. So you multiply the vector X after you do the matrix multiplication?
yeah, so yeah, you can do that. So you can do this multiplication in whatever order. So you can do this multiplication first, and this would be the matrix corresponding to, or matrix associated with T composed with S. Right. So, okay, let me write this out so hopefully it's clear. So if A is the matrix associated with T, and B is the matrix associated with S, right? Then A times B is the matrix associated with the composition T composed with S. And so something to keep in mind is that you multiply, if you want to, say, compute a composition function, you want to figure out what the matrix would be and write down the formula for your composition. You should multiply in the order that you would compose. So, or that you would write the composition in. Okay, so yeah, we're doing okay on time. Maybe I'll have I didn't find an example. I could make one up on the spot, but I'll probably just do one next time for this. To show how this works if we have particular matrices. I mean, it's essentially matrix multiplication, but maybe it'll make it more clear if we do an example. And we're almost done with 2.1, so we're just going to finish up with powers of matrices and transpose. Let's see. Right, so let's see. It means that, so I'll try to do this. So if T, say, maps R2, R, S maps R, F. Okay, so if you had two functions like this, we could compose these, but we would have to do, so for instance, S composed with T would map R3 to R3 and then, or wait, okay, so this is, okay, so first it would map R2 to R3 and then R3 to R3. So this is defined, right? The other way is not defined. So you could write this down in this way, and in order to find S composed with T, the matrix for it, you would just multiply. So say A has associated matrix A, S has associated matrix B, you would just multiply B times A to find it. Because S comes first in when you write down the composition and then T. So it's in the same order. Okay, so yeah, I promise I'll do an example next time to hopefully make this more clear. But yeah, we have just a couple more things. So if A is a square matrix, then we can define what this means is, or let me read that. A times itself is defined. If it was not a square matrix, that would automatically not be defined. But if it is a square matrix, we can write down powers of A. And so we'll just write it in the same way that we write powers of, anything else, numbers, just using an exponent. So A to the K will just be A times itself, K times. And by convention, so this is going to be similar to how exponents work for real numbers. So by convention, A to the 0 will be the identity matrix. So this is similar to how, I don't know, x to any, or let me use an actual number. So like 2 to the 0 is equal to 1. A proof for the identity matrix thing, no, because it's sort of, like I said, just convention. So we're kind of just defining it to be that. Okay, and now one more thing for this section. So we have something called the transpose. So in order to take the transpose of a matrix, basically you just switch the rows and the columns. Okay, so, and this is denoted A to the T. So we use this capital T for transpose. That's how we will write it. And let's look at an example. So if we have the matrix 1, 2, 3, 4, and we want to take the transpose of that, the column becomes the first row. So the first column becomes the first row. So it would be 1, 3. And then the second column becomes the second row. So 2, 4. So it will look like that. So it's almost like a reflection along the diagonal, the main diagonal. So another example, say we had just like A, B, C, D, E, F, G, H, I. We take the transpose. So the first row becomes the first column. So you A, B, C, D, E, F, G, H, I. So notice that the main diagonal does not change, right? Anything on the diagonal doesn't change. Everything else moves around, right? If you have a rectangular matrix, this still works. So the first row becomes the first column. So you'll get 1, 2, 3, and 4, 5, 6. So the transpose of so if A is an M by N matrix, A transpose is N by M because you switch the rows and columns. That makes sense though, because if A is invertible, going down. Right. Okay. Yeah. So we are out of time. So we'll leave it at that. That is all of the operations that we can do on matrices, and we'll just need to practice. Actually, there is one more thing I'll have to say, but I'll say it next time. So.